It is Wednesday, my dudes.
3, 2, 1. Oh shit. He's coming back on, isn't he?
In this video, we'll create rocket design data files for KingsRockSim. Rocket design data files such as the ones we've used previously, for example the LATV or Alpha Centauri or the Alpha Centauri control test. So we're going to run the program again because, like the simulation input data files, we can create the rocket design data files through running the program. Now, previously we've used meters and kilograms as our consistent length and mass dimensions, but in this case, if we open up SolidWorks, or if you want you can open up AutoCAD or whatever other CAD software you use, in this case it's SolidWorks. This is the Alpha Centauri rocket. Here you've got your nose cone, some body tubes, you actually have a transition here, another body tube, a boat tail at the end, and some fins, trapezoidal fins. But with this SolidWorks model, the dimensions we've worked with to create that CAD model were actually grams for mass and millimeters for the length dimension. So I've already entered 0 and 0 for meters and kilograms here. I want to change that to be millimeters and grams. So I'm going to have to restart the program. As the message tells you at the beginning, you can hit Control and C to terminate the program execution, then hit Run to start it again. We're going to change our options, enter 3 to use millimeters and 3 to use grams. We'll import a simulation input data file because we already know how to create that, but we're not going to import a rocket design data file, so hit No. And now it will start asking you questions about your rocket. Firstly, you want the total length of the rocket, and remember this is all going to be in millimeters now. So go to your CAD model, click on the tip of your nose, hold Control so you can select another part of the rocket, in this case the base of the rocket, and then we'll click Measure, zoom back out and find where it gives you your distance there. That's 1756.54 millimeters, so that's the number we want to enter into the trajectory simulator. And hit Enter. Next it will ask you for the surface finish of your rocket. Now in other rocket trajectory simulators you can actually select different surface finishes for different components, but for this one we want an overall surface finish. In this case we'll go with smooth matte paint finish, which is typical. So type 4 based on the key provided, and now a name for the rocket design. This is Alpha Centauri. We'll call it Alpha Centauri Mark II. It's the same rocket, we're just rebuilding it from scratch. And now you'll actually build up the rocket design from the tip to the bottom. So that will start with the nose, and as you can see from the key provided, you want to enter the number 1 to describe the nose design, 2 to describe the body tube. For canards, that's the same as fins, you want to type 4 for fins and 3 for transitions, and boat tails are also a type of transition in this case, so that will be 3. So we'll start with the nose, that will be 1. So go to your CAD model and you can select the nose there. We'll type 1 in the trajectory simulator for the nose. Now for Alpha Centauri we already know the type of nose in this case is tangent ogive, so from the key provided you can see that it's 3 for tangent ogive, so type 3 and enter, and then the dimensions of the nose. So firstly, nose base radius. We'll go to the CAD model, select the circumference of the base of the nose, and measure, and it will tell you the diameter. That's 58 millimeters, so you know the radius will be half of that. Now you can actually enter 58 divided by 2, and that will calculate it to be 29 as the nose base radius. Next you want the nose length. Back to the CAD model. Now we'll select both the base and the tip of the nose and measure, and that's 250 millimeters. So type 250 and enter. And finally the nose tip radius, but for this type of nose design you can actually see it's a pointed tip. so it's going to have a radius of 0. So if you go back to the program, type 0 and enter. Then we want to enter another rocket part since it's not just a nose. So enter Y for yes and enter again. It'll provide you with the same key as before. We know the next part going down from the nose is a body tube, so enter 2 for the body tube. And it'll ask you firstly for the tube diameter. So in the CAD model, select on the circumference and it will tell you it's 58mm. Alternatively, we know there isn't a transition there, so the diameter of the body tube has to be the same as the base diameter of the nose, and that was 58. Next, go back and find the length of that body tube. In this case it's 275mm, so enter that. And that's all you need for body tubes. Now hit yes again for another part. The next part is actually a transition. It's, in terms of the rocket itself, it's a bulkhead. This is the recovery bulkhead in this case. But in terms of the exterior view of the rocket, it appears as a transition. The front diameter does not match the rear diameter of the visible part of the bulkhead. So it's a transition. So we enter 3 for transition. And firstly we need the front diameter. Find that out from the CAD model. Select it, measure, and that's 58mm since it should match the body tube diameter that it's linked to. Then we want the diameter of the rear end, that's wider, it's 60. And then the length of the transition, so you can select the front and the rear and measure the distance between them. That's 7mm for this transition. We'll add another part. The next part is another body tube, so follow the same process for body tubes. This one is 200mm long and 60mm wide. The next part is also a body tube. One of the slightly strange things about this design is these two body tubes are not the same diameter. Now with some other rocket trajectory simulator programs, this would cause a problem. This might react like a bug in the program. They can't handle it. It's not a problem in this simulator. The rocket will be accurately represented. So I get the diameter of this new body tube, it's 57.9, and the length, being the longest body tube in this rocket, has a length of 924.4mm. As you can see, there was a circular section that looked like it was part of the boat tail design, because it was, but however it had a constant diameter matching the diameter of the body tube it was attached to, so I included it in the length of the body tube. Since you have to treat body tubes and transitions separately, even though that particular boat tail design is formed of what is essentially a small body tube and a transition following that. If you've got two body tubes linked together that are the same diameter, you can treat them as a single body tube. It will have the same effect in the program. We only have 2 parts left to add now. We can try either the fins or the boat tail. We'll just go for the fins now. So type 4 for fins. And now the first parameter we have to enter for fins is the shape. Now previously I mentioned these were trapezoidal fins, and at first glance they do look like they're trapezoidal. But if you look more closely, this actually has one additional side. There's a straight side at the rear. So the trailing edge of this fin isn't actually the long slanted side here, it's the short, straight, vertical side. So this actually doesn't count as a trapezoidal fin. So from knowing this, you can reevaluate your options. You can either, instead of selecting it as being a trapezoidal fin, you can create an image of the fin, a freeform image, say in Microsoft Paint. It has to be a monochromatic image when you save it, with the fin being black and the background being white, and you can then import that. That'll be in another video. Or you can enter coordinates for vertices on the fins, along with one base dimension, which will be the root length, and it will then scale the dimensions of the other side to match the base dimension and the coordinates you entered. In this case, it might just be easier for us, for this video, if we instead remove that short side and make the fins trapezoidal and save freeform fin designs for another video. So we'll do that by entering the sketch in SolidWorks and deleting that one short side and matching up the end of the long slanted side with the base of the fin. And now we actually have a trapezoidal fin design. So we can enter 1 for trapezoidal fins now. Next it will ask you for the number of fins at this position on the rocket. In this case it's 3. If we exit that sketch and look at the rocket assembly, you would see there are 3 fins. The next question is the distance of the base of these fins from the base of the tube to which they are attached. Now you can see, if we're treating the constant diameter portion of that boat tail as simply part of the body tube to which it's attached, the fins are actually at that distance away from the base of that overall body tube. Our distance is about 20 millimeters, so we'll enter 20. Next we want the thickness of the fins, so go back to the fin part model and find out the thickness. In this case it's 3.2 millimeters. Next, the root chord length, so back to the fin and measure the distance from point to point of the root chord. In this case it's 120 millimeters. And then the fin span. So back to the fin model, you now want the vertical height. Measure that. In this case it's 57 millimeters. And the sweep distance. Now for this simulator, the sweep distance is the length of your leading edge. That long slanted edge of a trapezoidal fin design. So you can just select that edge and measure it, and that's 89.5 millimeters. Next, the length of the tip chord of the rocket. That's that short length at the furthest point away from the rocket, 31 millimeters in this case. And finally, one that's a bit trickier to find, that's the mid-chord line length. You actually have to create a line in your sketch for that, linking the middle of your root chord to the middle of your tip chord. And the length of that line is the length of the mid-chord line. And that's 62.04 millimeters. And that was the last dimension that needed to be defined for the fins. It will tell you at the end which body tube those fins have been assigned to. So when you do construct your rocket, know that the fins that you create will be assigned to the last body tube you created. Now there were 3 body tubes in this rocket design, the last one, number 3, being the long one at the end to which the fins are attached. So that assignment has been done correctly. Finally, we'll add the boat tail, which again you can see from the key is taken as a transition, so that's number 3 to enter. So you just enter the dimensions like you do for any other transition. It will be the front diameter of the boat tail, the rear diameter of the boat tail, and the length between the front and rear diameters. So the front diameter is 57.9 millimeters, the rear diameter is 44 millimeters, with the length between them being 100 millimeters. hit enter. Now, that should be the rocket fully defined. If all your measurements have been done correctly, you'll be given the message that the rocket has been fully defined up to its total length. In which case, the program will now only let you add more fins should you wish to do so, but we don't. We only have one set of fins in this case. So finally, we can hit N for no to the question of adding another rocket part. And that is your rocket fully defined, your rocket design file created. There it is, Alpha Centauri Mark II. And there are all the numbers we entered. And if you compare that with the actual Alpha Centauri rocket design data file created previously and used in previous videos, the numbers should be very similar. Now you'll notice we also have components and component names files associated with Alpha Centauri. Those need to be created as well. They're done in a separate process within the program. In order to create these components files, you will be asked to enter mass and distance from the reference point data for each of the interior components of your rocket. Now for one like Alpha Centauri, that can take a while because there's a lot of interior components, and as you can see I've already done this previously. But for this video I'll simplify it by separating the rocket into three main components: the total dry mass of the rocket, that's every non-propellant component in the rocket, and then since this rocket employs a hybrid motor, we also have the liquid propellant and the solid fuel grain. So first we'll go to our CAD model and identify the total dry mass by hiding the fuel grain and the oxidizer from the model. So we'll just be left with everything else. And you can see from that, the total mass of the system has gone down by about 1 kilogram to account for us hiding the propellants. So back to the program, we'll hit no for entering the surface area directly, since that can be calculated based on the rocket design dimensions we entered previously. Enter whatever values you want for variables such as the wind speed and such. Then we get to defining the recovery system. So firstly, the number of parachutes, in this case we used 2, and so for recovery options you'll be asked to enter the diameter of your parachutes, starting with parachute number 1. So for the Alpha Centauri that was 0.762. For Alpha Centauri, the first parachute, that was 0.762 meters, and it had a drag coefficient of 2.2. He'll then ask you at what point is it deployed, under which conditions is it deployed. So the first chute was deployed at apogee, so enter 1 based on the key for apogee. And for the second parachute, it had a diameter of 2.1336 meters and a coefficient of 2.2, but it was deployed during descent at an altitude of 550 meters. So select option 4 for altitude and 550 for the value. Now as you can see, if you'll recall, we were supposed to be using millimeters, and for the parachute I've entered 0.762 meters. That's incorrect, but one way we can make it so we don't forget when we're actually putting this data together, if you don't want to do, for example, 550,000 millimeters for altitude, you can instead just type 550 multiplied by 1000 using the asterisk sign for multiplication, and the program will calculate that. And then you just continue running the program as normal and importing an engine file, selecting the method you want to use for calculating the center of pressure, the drag, and so on, until finally we get to the point where you are given the option to import a list of rocket design interior components. This time we'll hit no for that because we want to construct those files from scratch. So then you'll begin entering information for each of your components, beginning with a name for the component, which goes into one file, which will be, in this case, Alpha Centauri Mark II component names. We'll start off with the total dry mass. and that dry mass from SolidWorks is 2,384.66 grams. We can just copy and paste that straight in. The distance of the component from the nose tip. Now, the distance in this case is the distance to that component's individual centre of mass, which you can get from SolidWorks. Now, having used the total dry mass being treated as a single component, will actually make calculations for the centre of mass and especially the mass moment of inertia inaccurate later, so you do want to be specific with these components details. But for the purpose of this video, we'll just stick to the total dry mass so we have less components to deal with. So first you need to check the coordinate system you're using in SolidWorks. Make sure it starts with an origin being the reference point for our program, which is the tip of the nose. Then looking at the centre of mass information, you can see it's 983.13 millimeters from the origin, or the nose tip, in the Z direction based on our coordinate system. That is the calculated centre of mass of all of the dry components of the rocket. And then it will ask you, is it a solid or liquid propellant? Since it's the dry mass, that's no. And then do you want to add more components? Yes, because we need to add the fuel grain and the propellant. So we'll start with the fuel grain. We're going to need to go back to the CAD model and unhide the fuel grain so we can view its mass and its position, with the mass being 122.4 grams and the distance of its centre of mass from the nose tip being about 1500 millimeters. So we can copy and paste that in. And this one is a propellant, so hit yes. And then we just add the oxidizer. So type yes to add another component, oxidizer for the name, and then we'll unhide that from the CAD model to view its mass properties. With the oxidizer having a mass of about 850 grams and being about 1000 millimeters away from the nose tip. Hit yes for it being a propellant, and no to add more components since we're done in this case. And those are listed on screen with their calculated individual moments of inertia, which are summed to get an overall moment of inertia, which in this case will be wildly inaccurate because we haven't listed each of the individual components. We've done a simplification here with the total dry mass. And that is the entire process for putting together a rocket design data file. As you can see from the image saved here of the rocket design, its side elevation, we have Alpha Centauri with all its body tubes and transitions and its nose and its fins. Here's the component data file, which just has the mass, the location of the centre of mass, and the option for whether it's a propellant or not. And there's the list of component names. And that's how you create all three of those files.